Hi guys, Dr. DeFeo. What I'd like to do is take you through some slides to help clarify and or highlight and explain certain ideas and concepts, and especially some models that help depict the movement of energy and matter through ecosystems. Recall that you should have gone through chapter 3714 through 23 in doing your homework assignment, which I have answers for that I'll get to in a little bit. Something also to kind of keep in mind is that 37 is a chapter on communities and ecosystems, and it might be worthwhile, considering that the final exam is coming up in less than a month, that you take a quick look back at what we talked about in this chapter. We talked about community structure and dynamics, the differences between interest-specific, competition, mutualism, parasites, tropic structure, especially tropic structure, because in a little bit we're going to talk about how matter and energy affect the shape of our food chains, how producers lead to quaternary consumers, and why there's so few killer whales. And so what I'd like to do is answer this question: how does energy flow and matter cycle limit ecosystem health? Okay, so the first key point I hope that you got from the reading is that energy flows, right? And so what do we mean by energy flowing? Well, you start with photosynthesis, right? So radiant energy is able to get converted into chemical energy, which gets turned into heat energy, or more importantly, cellular work, right? So you have energy flowing. The Earth is a closed system to matter, but energy could come in and heat can come out. So what we mean by energy flowing is that it's really kind of going through the system, it kind of flows through and it goes out. Now, difference is that matter is recycled, right? So if you have a closed system, matter cannot leave the planet for most purposes. And yes, there are cases where comets come into our planet, yada, yada, yada. But more importantly, we can think of about planet Earth as a closed system. And so in order for living systems to live and die, you need to have recycled. And so you have chemical cycling. We are made of chemicals. Recall that there are many essential elements and minerals. We need nutrients. We need carbon for our sugars and our biomolecules. Phosphorus is in DNA, and also a key critical component to phospholipids, and nitrogen, of course, is in amino acids. And so the physical laws of the universe govern this process: how matter and energy is conserved, how the second law of thermodynamics and how entropy increases lead to the energy flow and chemical cycling. So what about where does it all begin? So recall that photosynthesis is a key first step. And in most ecosystems, we have what's known as primary production, which is the amount of light energy converted to chemical energy by autotrophs. Recall that autotrophs are those plant organisms that are able to conduct photosynthesis. And a few ecosystems that, like down deep in the hydro, some of these hydro thermal vents, you will have chemotropic organisms, those that are able to take mostly hydrogen sulfide and turn it into energy. And so they can use energy instead of chemical energy rather than light. But for most purposes, primary production is kind of considered the photosynthetic organisms. And as you can see on planet Earth, you can see where there's a great deal of our net primary production. Well, what does that mean, net primary production? Well, first of all, we have to consider how much total energy is produced or converted from light to usable chemical energy. This is the total energy. Now, of course, those organisms will need to use some of it for their metabolism. So you can kind of think of this as a chemical equation. Gross production minus work minus heat, and this is used energy, will give us our net primary production. Anything that's left over is usable in the ecosystem. So after it's used the sugars to do the things that plants need to do to reproduce, what we have left over is energy. And so you can see a lot of this over the rainforests of South America, many of the deciduous forests in the East Coast where we live. You have the Congo, Sub-Saharan Africa. You have a lot of the rainforests and the islands where New Zealand is, north of Australia. You also have coral reefs. Okay, some of this you can see, obviously there's some production in the ocean, right? And so if we look up here, you can see that the open ocean, even though it's the most massive, when you consider per gram of open ocean, there really isn't that much net primary production. Where you get most of it from is in coral reefs, estuaries, and of course tropical rainforests. Which is why, even though there's few coral reefs in the world, they do account for a large amount of net primary production. And so it's these primary producers that set the energy budget for the ecosystem, because recall, whatever comes in that's going to be used by the rest of the heterotrophs depends on these plants making chemical energy. And so what we have here is that energy supply limits the length of food chains. This is one important consequence in what we mean by setting the energy budget. So a plant has a certain amount of available energy. And the caterpillar will use some of that energy to do cellular respiration, to grow. And so many of this is used by the organism. And then some of it is released, feces, for instance. And ultimately, the rest of the biomass of this caterpillar will be eaten by a bird or will decay and be taken apart by detrivores. And if we look at this, what we notice is that you might have 1 million kilocalories. Remember, this is a unit of energy. And it's going to convert this energy. So the plants will be able to use that, but only 10,000 kilocalories of energy are remaining are able to be actually utilized and remained for use by our primary producers. And what we notice is that the primary producers will use about 9,000 kilocalories and only leave 1,000 of those primary producers and so forth, and all the way up here. And what we find out is that, only 10% of the energy is able to go between these tropic levels, right? So if you have our first tropic level, second tropic level, and so forth, you only have 10% being used. 90% of it's being, you only have 10% of it available to be used, while 90% of it is either used to do work or released as heat. And so that limits the amount of tertiary consumers, right? That's why you don't see as many snakes as you do grasses in the open prairie. That's why you see few American bald eagles flying over the range, because there's only so much secondary consumers or tertiary consumers, depending upon the organism, for it to obtain the required energy to go through a life cycle. This is important to consider given the fact that a lot of Americans, especially myself, love eating our beef and our chickens, but it's not the most efficient way to eat energy, essentially. It would be, because you lose 10% of our energy, by the time it gets to us, that initial sunlight has lost, a tremendous amount of energy has been lost through heat and through the work needed to keep these organisms alive. It would be much more energy efficient if we became vegetarians, although we would be missing out on some good burgers. But it's something to consider, given that methane is a huge greenhouse gas, and if we can get our caloric intake in other ways by reducing the amount of calories, we'd be lowering the cost of our food and ultimately lowering the cost of greenhouse gases. And so you could think about the environment as a giant engineering project. Engineering is all about inputs and outputs. And so what we have is a biogeochemical cycle. Okay, we have our abiotic reservoirs. These might include the atmosphere, minerals, rocks, and ultimately whatever matter that has come from planet Earth itself. So we have giant geological process, uplifting of continental shelves. We have a lot of movement and volcanic action that's able to take matter from deep into the core of the planet and move it up to the crust where we live. In any case, nutrients are available to producers, and the producers are able to provide energy for the consumers. And ultimately, the consumers will die off, and say, well, the producers and the decomposition will lead to recycling of the potential nutrients. Key along the way, of course, is the waste products that come from. So this is waste here, and this is really decomposition. What you have here is a lot of nitrogenous waste. One of the reasons why the zebrafish did not make it was because I did not change the filter enough to keep out the nitrogenous waste. And some people actually will actually use that very nitrogenous waste produced by fish to actually fertilize our plants. That's how much you get, because recall that one of the key elements of life is nitrogen and amino acids and nucleic acids and whatnot. And so this is often will be excreted as waste, and that, of course, will be recycled into our reservoirs. Some key compounds you should be aware of are nitrates and phosphates and carbon dioxide. All of these are waste products, and they all help to replenish it in terms of the carbon, nitrogen, and phosphorus cycles. You also have to consider that there's global patterns of gas movement through the atmosphere. And then at the local level, we have minerals, and phosphates really only move in very local environments. And so when we consider all of the different cycles, it's important to have the schematic that you really do have these four systems where you have the producers converting a lot of these nutrients. So, for instance, bacteria are going to be really important to provide the available nutrients for producers, and so forth through the cycle. And so let's look at them in more depth. The carbon cycle depends on photosynthesis and respiration. Photosynthesis will provide sugars, right? And sugar will have carbon. Carbon is a critical element of life. You also have respiration, which is going to add to carbon dioxide, which of course is going to help photosynthesis. Use that and convert and fix that carbon into sugar. Many of these sugars will be eaten by primary consumers, and those will consume the primaries, and ultimately waste and death will be taken care of by detritus fungi and bacteria in the soil, and a lot of the soil microbes will help decompose those even further, and this will fertilize our soil, providing good, what's known as humus. Is important because it's able to hold on to key minerals in our soil, which will help our plants grow, and the cycle begins anew. And a key thing to keep in mind is that carbon will move from the environment to organisms where it's used to build key biomolecules. Don't forget about these: carbohydrates, proteins, lipids, nucleic acids. Carbon's also used as a storage compound in cell formation in all organisms. So it's really important to understand the implications of this. And we are, of course, adding carbon dioxide to this atmosphere, which might be good for the plants. There are some other secondary effects, such as warming of the environment, which is a whole completely other story altogether. But the carbon cycle is very important, and the key processes here to keep in mind are photosynthesis and respiration. Phosphorus. Phosphorus is an element. Phosphorus is the element. But phosphate is really how it's active in the environment. Phosphate is a compound ion, so it's a molecular compound, but it has a charge. And these phosphates are able to come out of rocks. Of course, acids will remove some of them, and many fungi will produce these. And if you saw in your hike that there are lichens, lichens will also help to take apart minerals within the rocks themselves. But phosphates are locked away. The reservoir of phosphate is in rock, right? And so weathering of the rock will allow phosphate ion to get into the soil. But because it's there's so few of it, and because it's soluble, a lot of times the water is going to kind of flow. If there's too much phosphate in the soil, there will be a lot of phosphate in solution, and this can contribute to what we'll see polluting our rivers if there's too much phosphate. A lot of fertilizers, for instance, produce the amount of phosphate that's in the soil downstream, for instance, of farms. In any case, the inorganic phosphate will get assimilated by plants. Plants will be eaten by animals. Animals will die off, the detritus, and the phosphate can return to the soil itself. But again, a lot of it is quickly lost to our waterways. And so we rely on external sources of phosphate, either through rocks or through fertilizer or artificial ways. Important points about phosphate is that it's an ionic compound, and it's important in nucleic acids. Remember, phospholipid biomembrane. So if you have your head group, let's remember what lipids look like. Your tail, the head group is where the phosphate is. Okay. And the last cycle that we're going to be interested in is going to be the nitrogen cycle. And in this one, whereas the fungi, I didn't even talk about the fungi. Very important. So yes, acids break down the phosphates into the soil, but mycorrhizal fungi form a symbiotic relationship with the root systems of plants. Now, all of this is actually fungus. White, wispy strands of filamentous fungus. And these fungi are really good at facilitating phosphate uptake. And you might often see around trees, especially after it rains, a ring of mushrooms, and mostly because underneath the soil you have a tremendous amount of these networks of fungus, and these fungus are really, really important for tree health and forest cycling of nutrients in the forest. And I think on Tuesday, hopefully, if the timing works out, we're going to watch a really fascinating story about how trees communicate through these fungal networks. So if there's one takeaway from here that you must know, it's that mycorrhizal fungi are very important in movement of minerals in the soil. Now, in the nitrogen cycle, it's not fungi that's important, but bacteria. Remember, fungi are eukaryotic, but bacteria are prokaryotic. And the key thing to do here is that we have tons and tons of the abiotic reservoir for nitrogen is the atmosphere. Only problem is that we living things cannot easily access that nitrogen because nitrogen N2 is a very, very stable compound, a molecule. You'll learn about that next year in chemistry. And so what needs to happen is that the nitrogen needs to be fixed by bacteria. And these tend to be in these root nodules of plants, right? And so nitrogen fixation is the atmospheric conversion into ammonia and many different nitrates. And so there's a lot of bacteria in the soil. It helps to increase the concentration of our ammonia in the soil, and this will be assimilated by plants. Plants will be eaten by animals. Waste and decomposition will take place. You also have other bacteria that produce, that not only fix nitrogen into ammonia, but will then take that ammonia and help increase the nitrates in the soil, and some plants are able to utilize that, and that feeds into the system. So there's two mechanisms. There's the formation of ammonia in the soil through nitrogen fixation, and converting ammonia into nitrite by nitrifying bacteria allows us to have nitrogen, and plants will get it for their amino acids and their nucleic acids. We will eat them for our important biomolecules. And the cycle is completed with bacteria that actually denitrify, so take the nitrates out of the soil and turn it back into nitrogen. So we have a complete cycle of this working through. And one key important point is to remember where nitrogen is and what it's used for, a key element in proteins and nucleic acids. And we can think of bacteria as key nitrogen fixers. They're able to fix nitrogen, in other words, use it from something that's unusable to something that's usable. And you do this through fixation. If you recall, we talked about carbon fixation. That's what photosynthesis, that happens during photosynthesis. This is nitrogen fixation. Now, even though nitrogen is limited in the soil, what we as humans have found out how to do is to use a chemical process to make lots of nitrogen available in the soil, fertilizers. And it's really remarkable when you look at this. So here's the Mississippi River, and all of these other rivers flow into the Mississippi. Much like many of the rivers in the Northeast flow into the Chesapeake Bay, you have this river delta here. And all of this river concentrates down in New Orleans. And what do we know is in most of the central United States? Farmland, right? And a lot of the time we're going to use phosphorus and nitrogen fertilizers. And so you say, well, it's great, you know, we're growing a lot of food, but unfortunately, we're also destroying our fish habitat. Because what will happen is that many of this leftover phosphorus nitrogen, because many of it's not actually, we're putting so much on the soil that many of it's not actually used by the plants. It just goes into the water systems. And when it goes into the water systems, there are cyanobacteria that are able to utilize that much, very, very quickly. And when it does that, it forms basically a blanket of bacteria over top of the water. Now, if you can imagine what that would look like, right? If you have our water here, and you have this very dense layer of cyanobacteria, right? For one, you're going to limit sunlight. Okay, so you're affecting the sunlight, which is going to, of course, affect the temperature of the water and other local abiotic aspects of it. But more importantly, what will happen is that eventually these will die. And as they die, they decompose. And part of the decomposition process is that oxygen in the water will end up leaving. So you'll have very little oxygen in here because the decomposition process uses up all of the oxygen. Now, if there's no oxygen in water, there's also no oxygen for, so lack of oxygen means no oxygen for fish. And so what we have are these known as these dead zones where there's very, very low dissolved oxygen in the water. Oxygen doesn't readily dissolve in the water. It requires quite a bit of agitation. And as you recall, one of the adaptations that fish have is to move water over their gills. And so they have very special adaptations to squeak out as much oxygen as they can. But if we reduce that oxygen even more through artificial ways, through a process called eutrophication, we're going to have problems in our waterways. And so there are a lot of unintended consequences to some of these great technological innovations that we had that we need to keep in mind. And finally, let's keep in mind something here. All of these processes, if we go back to our biogeochemical map, right? All of these this is a self-contained system. If we start reducing producers and consumers, we're going to seriously deteriorate our biogeochemical cycles of our nutrients. This could have tremendous consequences on biodiversity and our own ecosystem services that we receive from them. So, for instance, the fresh water provides us food and fish and shellfish. Natural vegetation, if you imagine the river, right? And we have our tree. And we have many things living on the river. We have lots of different sorts of plants and species of plants. And what happens is that the bad stuff, the nitrates and the phosphorus, come down. But guess where most of it goes? Most of it will go into our plants. All right, it gets captured into our plants, preventing it from going into our waterways, okay, making our water very clean. And so in a way, we're able to filter away a lot of this harmful stuff that's going into our things. So we also have found ways to filter water using water treatment plants, and that costs money. But if our environment does it for us, then we don't have to spend as much money in our economy on treatment plants. So there is a cost to all of this. So this fertile soil helps to prevent landslides, mudslides. We're able to recycle nutrients, decompose waste, regulate climate. You can imagine if you have giant forests, if you chop down those forests, now you have dirt, and then you have wind going through, and what does the wind carry away with it? Water, which means it's going to be harder to grow. And that's going to limit our ability to use the soil effectively. We have wetlands that buffer coastal regions against hurricanes and reduce the impact of flooding. All of this stuff would cost us engineering. We could probably figure out how to solve it. It costs a lot of money. Nature does it for us for free. And finally, recall that abiotic and biotic features limit the carrying capacity of a particular population. So by messing up these cycles, we might affect our carrying capacity, which was a population, the number of individuals that environment can sustain. So we can ask this really important question at the end of this lesson. Why is there interdependence in nature? Why do we have these very complicated food webs? Well, one of the answers is that it's required in order to effectively cycle our chemicals throughout the ecosystem. Earth is a closed system. Without our biodiversity, we're going to limit the ability to use nutrients, and it's going to ultimately limit population. So in your final research project, you need to consider how your carrying capacity is going to be affected, possibly by changes in nutrient cycling, changes in your trophic levels in that local ecosystem. Without certain producers, you're going to have tremendous consequences for our keystone species. So it's really important to keep in mind the big picture here, and that interdependence in nature is critical so that we can get cycling of matter through our environment, maintaining our population growth for those organisms that need it. Now, there are seasonal and normal earthly cycles. The problem is that right now with humans is that we are really affecting our carrying capacity at a very fast rate, not only for endangered species, but soon to be endangered species. All right, so I just wanted to show you the answers to the questions. I'm not going to kind of read through them. I'll let you look at it real fast. So I would check your answers right now. I like this one here, borrowing of chemical elements from the earth because they will eventually be returned. This is important here. Only a fraction of the energy in the biomass is available to them. Remember, if you're losing 10%, by the time you get up to the tertiary and quaternary predators, you're going to lose a lot. This is a really neat quote. 1,000 tons of grass. Can you imagine the amount of area needed for that to happen? That's a huge amount of land. So not only is a huge amount of land needed for just 300 trout to support one person, imagine our whole entire world using it. How many millions upon millions of people using? Interestingly about trout is that we eat cattle, but trout are actually secondary consumers, which are higher up on that list. And so as healthy as fish are for us, and in terms of energy, it's even less efficient at converting sun energy into energy that we need to survive. Here's that biodynamics, nutrients available to consumers. Consumers feed on it, release as waste, breakdown of organic matter.